when is there a rational point? Or, I mean, equivalently, when is there not a rational point? But mostly, again, I'm going to concentrate on sufficient conditions. So we want to find conditions on X that guarantee existence of a rational point. So goal for K, a function field of a curve over an algebraically closed field. Over some algebraically closed field, little k, find sufficient conditions on X, and they should be geometric conditions, which means they should really be conditions on the base change to the algebraic closure from capital K to its algebraic closure, guaranteeing guaranteeing existence of a rational point, guaranteeing xk is not empty. And I mean, of course, there are all sorts of different conditions. You could start with a point and project the space and then fix X to be some subvariety that contains the point. That would certainly do it. But the goal is to find some sort of intrinsic natural condition on this fiber guaranteeing existence of a section. And then what we saw yesterday, Sin's theorem, gives one answer. And I'll mention a couple of other answers. So Sin's theorem is one answer. If X in P in K is a hypersurface of degree d less than or equal to n, then xk, X has a k rational point. So that's one answer. But actually, Brendan showed you another answer last week. So there's a theorem proved partly by Manin and then finished by Colliot-Tolin that if X is a rational surface, so I mean, again, what I mean by that is not necessarily rational over K, but it's base change. So let me make that clear. If the base change is a rational surface, then X has a rational point. And the proof of this is a very nice use of the mental model program over non-algebraically closed fields. If you have a rational surface, then the mental model program tells you how to turn it into a simpler surface, and you'll either obtain that X is a conic bundle over a conic over K, and then you can apply Sin's theorem twice. So I mean, I'm sorry, I didn't mention this before, but there's, let me just, aside. This will come up tomorrow. This will be very important tomorrow. Given a division algebra, or I mean more generally given a central simple algebra, A over K, there are these things called Brouwer-Savary varieties. There is an associated variety or maybe Savary-Brouwer, I don't know. People use both notations. And this represents a functor. So there's an associated variety over K. And what functor does it represent? Representing the functor. So for every extension, L over K, the L points of this guy are in one-to-one correspondence with the right ideals inside of the base change, I a right ideal, whose dimension as an L vector space is, if this is so the dimension of A is n squared. So you look at the right ideals of dimension n. And I mean, to understand what's going on here, when you base change to the separable closure, of course, A just becomes some matrix algebra, the n by n matrices over K. And now what are the right ideals inside of the n by n matrices? You fix some subspace of your n-dimensional vector space, and you look at those matrices whose images contain in that subspace. And that's the set of all such matrices is a right ideal. And so if we fix that the dimension of the ideal should be n, that means that subspace we're fixing is one-dimensional. Oh, so we're looking at one-dimensional subspace of our fixed n-dimensional vector space, which is projective space. So when you base change this Brouwer-Savary variety to the separable closure of K, it's just a projective space. So it's a twist of projective space. So this thing is a twist of projective space. Projective space Pn minus 1. And you can go in the other direction. I mean, if you have a variety defined over K whose base change to the separable closure is isomorphic to Pn minus 1, then it always comes from a central simple algebra. So there's a one-to-one correspondence between these Savary-Brouwer varieties and these division algebras. And if you look at what Sin's theorem tells us, that the only division algebra over the function field of a curve is just the function field of the curve itself. So it says every central simple algebra is already a matrix algebra, which means that this Savary-Brouwer variety already has a point. So one equivalent way of stating Sin's theorem is to say that every Savary-Brouwer variety over the function field of a curve has a point. And the most common application of that is every conic over the function field of a curve has a point. So if your surface is a conic bundle over a conic, then the conic has a point. And then when you restrict that conic bundle over that point, it's again a conic over the function field of a curve. So it also is a point. So the conic bundle over a conic case just follows from Sin's theorem. And then the other cases are Del Pezzo surfaces, which you have to do one by one. So Brendan talked about this last week. So this is one other answer. Now let me tell you a third answer. So Chevalier and Springer proved that every homogeneous variety for a connected linear algebraic group over the function field of a curve has a point. Every homogeneous variety for a connected linear algebraic group has a K point. And I mean, let me point out that actually these two theorems hold if you replace the function field of a curve by any C1 field, then these two theorems also hold. So the question is, is there a common generalization of all of these three things? So the first one, we look at low-degree hypersurfaces in projective space. The second one, we look at rational surfaces. And the third one, we look at homogeneous varieties. Is there some commonality? And the second and the third, there's an obvious commonality, which is that they're both unirational. So, I mean, while the first one is rational, the second one, well, it's at least unirational. So I'm not actually 100% certain whether those things are all rational. But the second and third examples are unirational. What does that mean? So a variety X is unirational. I should say over a field, but I mean the base change is over K bar is unirational if there exists a dominant rational transformation from projective space to the variety. So it's a quotient of projective space, dominant rational transformation, Pn to the variety. So it's dominated by projective space. And the first, well, I mean, it's even rational. So this, in the first case, this dominant rational map, you can choose it to be generically finite of generic degree 1. And in the second case, well, it's a homogeneous variety for a connected linear algebraic group. Every linear algebraic group is rational. So it's a quotient of a rational variety, so it's unirational. But the first case, it's actually unknown, so this is an open problem. But the suspicion, the strong suspicion, is that most of these hypersurfaces are not unirational. So open problem is every, let me say, smooth hypersurface X in Pn of degree d less than or equal to n, unirational. And again, I think Fano, quite a long time ago, conjectured that they are not all unirational. I mean, I can tell you which ones are the lowest case where they're expected to not be unirational. So expectation, if D is 4 and N is 4, a very general such hypersurface is expected to be not unirational. But we don't know how to prove that. I mean, there are lots of techniques for proving varieties are not rational, but none of them apply to prove a variety is not unirational. A very general hypersurface is not unirational. Let me mention, I mean, if D is strictly bigger than N, then it can't possibly be unirational. So there's an invariant, which I'll talk about in a few minutes, called the codirac dimension. When D is bigger than N, then the codirac dimension is non-negative, and every unirational variety has negative codirac dimension. When D is less than or equal to N, these guys do have negative codirac dimension, so that doesn't rule it out. And you keep going through the list. You keep coming up with invariants, and every time you think you've got a way of proving that this variety is not unirational, it turns out that the invariant doesn't distinguish between these hypersurfaces and unirational varieties. So this is a very frustrating problem, but this is what people expect. There's some reason to expect this. So that's the expectation. So what can we use instead of unirational? And there's another property that, as my understanding is that it was considered quite a long time ago, but it was really intensively studied only since the early 90s, and that's called rational connectedness. So rational connectedness is an analog in algebraic geometry of path connectedness. So a topological space is path connected if whenever you have 2 points, you can find a map of the interval into that a continuous map of the interval into that topological space, mapping the endpoints of the interval to those 2 points. And the idea of rational connectedness is you do exactly the same thing, but you replace the interval by P1. So let me just tell you the definition. So, well, let me assume that my variety is smooth, projective, and non-empty. Variety X over a field, over an algebraically closed field, say. An algebraically closed field K is rationally connected So there's going to be a lot of equivalent definitions, but let me tell you the original one first. So it's rationally connected if there exists an irreducible variety M and a morphism U from M cross P1 to X. So let me just stop here for a moment. So in other words, what do we have? We have a family of morphisms from P1 to X. Every point in M parameterizes a morphism from P1 to X. So that's how you should think of this morphism. It's just a family of morphisms from P1 to X. In fact, you could use Hom P1X here instead of M, or at least some irreducible component of it. But there's some condition you want this to satisfy. So there's a morphism. If you have a family of maps from P1 to X, then what you can do is you can fix 2 points on P1 and then look at where the map sends that pair of points. That should be a point in X cross X. So it's a morphism such that the induced map, so well, let me just introduce some notation here. So this will be a point little m, and then t goes to some, and then f sub little m t. I mean, if we fix little m, then we get a map f from P1 to X, and then t maps to f sub little mt. So it's a morphism such that this induced morphism so this is the morphism that sends m s t to the pair f sub m of s, f sub m of t. So again, M parameterizes a family of maps from P1 to X, and then given one of those maps and a pair of points in P1, we get a pair of points in X, and that's all that this map is. And the condition is that this map is surjective. So this is a convoluted way of saying something very simple. So let me say it slightly false, but the way that people think about this is to say that for every pair of points in X, there exists a rational curve in X containing those pair of points. So that the short version that's not quite accurate. So the brief version is that X is rationally connected. So I'll just write RC for rationally connected. If for every pair of points, PQ in X, let me say K points, there exists a morphism, of course, depending on the pair of points, such that f of such that P and Q are in the image of F. I mean, we're certainly getting that out of this definition. If you take a pair of points PQ and X, so a point PQ inside of here, since this map is surjective, there exists some Fm and some pair of points S and T in P1 such that Fm of S is P and Fm of T is Q. In other words, P and Q are in the image of Fm. So that certainly follows from this one. They're almost the same, but not quite. So if K is uncountable, then these are equivalent. Yeah, that's kind of crazy, isn't it? These are equivalent. But they're not always equivalent. So there are examples by Bogomolov and Schinkel showing that these are not always equivalent. I mean, what can happen is you can have a variety defined over, say, the algebraic closure of a finite field. And the algebraic closure of a finite field is still a countable set. So the point is that these families of morphisms come in, these morphisms from P1 to X come in families. Typically, to specify this morphism, what you would do is you would look at the graph of the morphism sitting inside of P1 cross X. That's a subvariety of P1 cross X. We're assuming X is projective, P1 is projective, so the product is projective. You fix some ample line bundle on P1 cross X. For that subvariety, you look at its Hilbert polynomial, and if you specify the Hilbert polynomial, the set of morphisms from P1 to X, whose graph has that Hilbert polynomial, is a nice finite type quasi-projective variety. But there are countably many Hilbert polynomials. So that space of maps from P1 to X has countably many different components. And for each one of those components, you might sweep out just a subvariety of X cross X. But if X has only countably many points, for instance, if your algebraically closed field is countable, then it could happen that these countably many subsets, even though none of them is surjective, altogether they are surjective. So that's what's happening in these examples. So there are examples by Bogomolov and Schinkel showing these are not necessarily equivalent. They're not always equivalent. But if you base change to an uncountable field, then they're equivalent, not always equivalent. Or we could, instead of just using closed points, we could also use generic points as well. And then if we state this the right way, then they will be equivalent. Anyway, so this is the strongest form of this definition, but there are weaker forms and that are also very useful. So this is probably going to be too low, so I'll only use the top half of this board. So equivalent formulations. So one thing is, we don't need to assume this is surjective. It suffices to assume that it's dominant, that the image is dense. So one suffices to assume one of the most important things, I have to say this. So again, this notion has I mean, at least according to some people, been around for a while, but this was sort of reinvented and intensively studied independently by Campagna and also Kolar, Mioka Mori in the early 90s. And I'll tell you why they were considering this in a little bit. But everything I'm saying now, these are results of Campagna and Kolar, Mioka Mori. So here it's the first one is that you can assume something weaker. It suffices to assume U2 is dominant. So it doesn't have to be that for every pair of points you have one of these curves, just for a general pair of points. And then it in fact follows that, well, for some other family of maps from P1 to X, you'll get the result for every pair of points. So that's one thing. Another thing is that you can get something stronger than this. So this strong condition is equivalent to this weaker condition. It's also equivalent to this much stronger condition for every. So I'm going to use the brief version. I mean, it's a good exercise for you to figure out how to make this precise in that sense. But let me just use this notion here. For every finite set of points, P1 through Pn in X. I mean, for every integer n and every finite set of distinct points. And moreover, every choice of a tangent vector at each of these points. So choice of some element in the Zariski tangent space of X, there exists a morphism from P1 to X such that all of these points are in the image. The morphism is an immersion at each of these points, and the tangent vector is in the image of the derivative map, such that P1 through Pn are in the image. I mean, you can even specify which points in P1 map to these points, but such that these are all in the image. And for every I, this tangent vector, Vi, is in the image of the derivative map, is in the image of the derivative map. I mean, at the preimage of Pi. Let me just write it Pi. So you get to choose the points and the tangent vectors, and then I can find a rational curve that passes through those points with those tangent vectors. That's what the moral is here. So let me put this up. Move this down. So these are all nice, but there's one reformulation, I mean, one equivalent formulation that's nicer than all the others. I guess I have to move it. It's a local condition. So the problem with unirationality, this property here, is that it is very hard to determine whether a variety is unirational or not. Well, in one direction, it might be very easy. I mean, if you start with a variety that's presented in this way, then it's obviously unirational. So you can hope to just luck out and find this sort of a morphism and prove that it is unirational. But if you suspect your variety is not unirational, again, we don't have any way of proving that finding any rational. Yeah. So this open problem here, instead of using low-degree hypersurfaces, you could put in the words rationally connected variety. So is every smooth, yeah, and I'll explain why that has anything to do with what I'm erasing in just a second. Is every smooth rationally connected variety unirational? Unirational. And we don't know. I mean, again, the suspicion is no, that most rationally connected varieties are not unirational, but we don't know. That sort of illustrates the point that unirationality is a difficult notion to work with. But rational connectedness, I mean, it's not obvious from the definition that this is any better. I mean, you have to check something for every pair of points. So how is that necessarily any better than the original definition? But it turns out that you don't. So there's a local criterion for rational connectedness, which is the following. So X is rationally connected if and only if, well, first we have to assume X is connected. I mean, if it's rationally connected, it's obviously connected because, well, I erased it. I don't know where the definition is. Oh, it's up there. That M is irreducible. And then we have this map from M cross P1 cross P1. M cross P1 cross P1 is irreducible. and then it surjects onto x cross x. So x cross x is irreducible. That surjects onto x, so x is irreducible as well. So if it's rationally connected, then it's irreducible. Of course, we're assuming it's smooth, so irreducible is the same as connected. But then the second condition, the important part, is there exists a morphism, a single morphism, f from P1 to x, such that when I pull back the tangent bundle of x, this is ample. So this is isomorphic to, so it turns out that every locally free sheaf on P1 is a direct sum of line bundles. That's growth index lemma. It's very easy to prove. And then the line bundles on P1 are just the tensor powers of Serre's twisting sheaf. So every vector bundle can be written as a direct sum of line bundles. And the condition here is that each of these AIs are positive with all AI bigger than 0. So both directions in this are not obvious. So if you have this condition over here, why does this hold? Well, actually, it's not obvious, but it's not hard. If you imagine that you take that pair of points, P, Q, and then you vary them. So in other words, what does it mean to vary a point? Well, to first order, it just means you choose a tangent vector. Yeah, I'm going to hold on to these so I don't drop them again. So you choose a tangent vector. Here we go. And then you want that as you move your point along that tangent vector, the curve should move as well. So the an infinitesimal consequence of this definition, the two-point condition. So if you move your curve to first order, that means if you have a one-parameter family of curves, then, and you look at one of the fibers, and you look at the derivative, the derivative of that one-parameter family, what that is it's a normal vector field on the curve, or equivalently, it's a tangent vector field on the curve. So it turns out that the infinitesimal consequence of this two-point condition is that the map from the pullback to just evaluating at these 2 points, so evaluating at P and evaluating at Q, is surjective. So again, what this is saying is that if you move P, so you choose a tangent vector, a first order movement of P and a first order movement of Q, then you can find a first order movement of the map, which again, that's equivalent to an element in this, to a global section of the pullback of the tangent bundle, which matches those two conditions there. So it means this is surjective. And then if you look at vector bundles on P1, again, they can always be written as a direct sum of line bundles like in this way. And if you look at those vector bundles that satisfy this condition, they're precisely the ones where all the AIs are positive. So that's one direction. The other direction is a little bit more complicated. It involves just a little bit of deformation theory. So it's not that hard, but it's a little bit more complicated. It's the other, I won't prove the other direction. The other direction uses some deformation theory. But again, I'm going to use something like this very soon in the proof of the main theorem. So this is rational connectedness, and this condition is very easy to check. You take your variety, you find this one curve, P1, and that implies it's rationally connected. So it has only to do with sort of the infinitesimal neighborhood, the first infinitesimal neighborhood of a single curve. So it's very checkable. There are also a lot of important properties. These are equivalent reformulations of the definition, but there are some important properties. Well, I'm erasing the connection of this definition with the Sin's theorem. So it turns out that every Fano manifold is RC. So let me tell you what this means. So we have our projective smooth manifold, projective smooth variety X. We can take the tangent bundle of X, and then we can take the line bundle we get out of this. So we take the top exterior power So this is now a line bundle, an invertible sheaf, or equivalently an invertible sheaf on X, and the condition is that this is ample. So X is phono if this guy is ample. And then what Kolar, Miyoka, Mori, and Campagna proved is that every phono manifold is rationally connected. And then the connection with these hypersurfaces is that if you take a degree D hypersurface in Pn, then this bundle here, so this is degree D, that's what that little d there means, is isomorphic to n plus 1 minus d, restricted to X. So this invertible sheaf, n plus 1 minus d, is ample on Pn. Well, I mean, there's some Lefschetz hyperplane theorem, so this will be ample on, well, you don't need that. This will be ample on X if and only if it's ample on Pn. And then this thing is ample on Pn if and only if this number is positive. In other words, if and only if d is less than or equal to n. So that inequality that comes up in Sin's theorem, d less than or equal to n, that just is what you need to make that parameter count work. It has some intrinsic geometric meaning. It means that the tangent bundle is positively curved in some sense. So it's a phono manifold. And then they prove this more general result that every phono manifold is rationally connected. So as a corollary, every smooth hypersurface with d less than or equal to n is rationally connected. This is one consequence. There are a couple of other, one property. Another property is that the image of more generally, if you have a dominant rational transformation, then if X is RC, then Y is RC. Now also, of course, Pn is RC. If you take 2 points in Pn, there's the line between those 2 points. So Pn is rationally connected. And then this says that if you take any, so you let X be Pn, and then Y be some variety, any variety which is the dominant image of a rational transformation from Pn is rationally connected. So this is a very, I'll show you one or two more of these to convince you of this. This is a very robust generalization of the notion of rational. So these are varieties that are close to being rational. When you have that trichotomy of curves, the simplest curve is P1. And then when you go to higher dimensional varieties, you want to find out what are the analogs of that extreme case in that trichotomy. And a very robust notion is rational connectedness. So this is another point. Another sort of robustness test here is that if X to B is a family of smooth projective varieties over a connected base, B, so this is in other words, it's a smooth projective morphism, and then you think of the fibers of this morphism as being varieties parametrized by the points of B. So it's a family of varieties parametrized by the points of B. Then if any fiber is rationally connected, then every fiber is rationally connected. So what this is saying is if you have some family of smooth projective varieties, the property of being rationally connected is constant in that family. If it's true for one, it's true for all of them. So again, we don't know that. Even for rationality, we don't know that. But certainly we don't know that for unirationality. So these are all examples of things that if you tried to prove the analog for rational or unirational, then, well, we don't know. It's very hard. But most of these are fairly easy for rational connectedness. So this is a much easier, much more workable notion than rationality. But there's one sort of hole here. So what about the other direction? If Y is rationally connected, then is X rationally connected? Obviously not. If you take any n-dimensional variety, you can find a dominant map from that variety to Pn. And Pn is rationally connected, but X doesn't have to be rationally connected. So is there something that would give you that. And so here's the question that was considered by these guys. Let f from x to y be a surjective morphism of smooth projective varieties. So we assume that the target y is rationally connected. But we also assume that a general fiber is rationally connected. So in particular, a general fiber is connected. So if you take that generically finite morphism from x to Pn, it doesn't have connected fibers unless x is rational. So that will rule out those cases. So assume y is rationally connected and a general fiber is rationally connected. And then the question is x rationally connected? So, I mean, this is, if you go back to that analogy with topology, where this is supposed to be the analog of path connectedness, if you have a vibration of topological spaces, if the base is path connected and the fibers are path connected, then the total space is path connected. So you would definitely expect that this is true. And that was the conjecture. So, I mean, in fact, there's a stronger version of this. So let me explain a different question that is very related to this question. So same setup. Be a surjective morphism of smooth projective varieties. And let's assume that y is a curve. There's a connected curve. Then the question is, does there exist a section? So this, you could phrase this as saying, if you take the generic fiber of this thought of as a variety defined over the function field of that curve, then does it have a rational point? So is there a section? So this is the integral model version of the question of existence of rational points. So is there a section S from y to x of f? And so we have some evidence that there is. I mean, namely those examples that I wrote at the beginning of the hour. If the general fiber was a hypersurface of degree d less than or equal to n in Pn, or if the general fiber was a rational surface, or a conic bundle for that matter by Sin's theorem, or if the general fiber was a homogeneous space for a connected algebraic group, then in all of these cases, the answer is yes, and then motivated by that, Kolar-Miyakomori conjectured there is always a section. And I mean, again, this has a number of consequences which I want to mention. So, I mean, it's very interesting from the point of view of rational points, but it's also very interesting from the point of view of geometry. This is what I said yesterday. If you guys as number theorists come up with something to say about rational points, this will be algebraic geometers will love you because these kinds of statements have some consequences, which I'll explain. So, but first let me just tell you the theorem. So Tom Graeber, Joe Harris, and I proved this a while ago. This is true. So I want to tell you about the proof, which it's, again, I mean, as the theorems in this area, it turns out to be fairly simple once you have just the basic elements of the proof. But first, let me tell you a few of the consequences and then sketch the proof. So, or can I still use one of these boards? Yeah. Oh, I'm sorry, the general fiber is rationally connected. Let this be a surjective morphism of smooth projective varieties. Assume y is a connected curve and a general fiber. Yes, of course, not every morphism to a curve has a rational section. And assume and a general fiber. So the geometric generic fiber is rationally connected. And yeah, what does this second question have to do with the first question? So the point is we want to know whether or not x is rationally connected. Now, we choose two general points in x, so we're going to use our equivalent formulation where we don't have to check this for every pair of points, just two general points. So we take two general points in x. They map to two general points in y. We're assuming y is rationally connected. So there exists a rational curve in y passing through those 2 points, the images of those 2 points in y. Now we restrict this morphism over that curve. So we just take the inverse image of that curve. We look at that fibration. Now it's a fibration over a curve. And the hypothesis is that a general fiber is rationally connected. So it's a fibration over a curve that satisfies these hypotheses. And then this theorem tells you there is a section, but there's more. So let me tell you some of the consequences of this theorem, which will then finish up this little discussion about the first question. I mean, it turns out that not only is there a section, but there are lots of sections. So there are a number of consequences, and Kolar-Miyoka-Mori knew all of these consequences. The only thing that was missing was the proof of this conjecture. So let me just tell you some corollaries, which again are due to those guys, not us. But you don't just get one section, you get lots of sections. All of this chalk is tiny, so consequence 1. So it's that same setup. We have a fibration over a curve. So f from x to y be a rationally connected fibration over a curve. So just one of the morphisms satisfying that hypothesis. Then what the theorem will tell you is that there exists one section, but what these guys recognize is let y1, y2, well, any collection of points actually, be distinct points such that the fibers xy1, xyn, so the inverse images of these points, that's the fibers, are smooth. So not every fiber will be smooth. You wouldn't expect that. If you have a family of elliptic curves, then they specialize. They can become nodal plane cubics, or, I mean, there's this Kodaira classification of the types of singularities those specializations could have. So you expect some of the fibers will be singular, but the generic smoothness theorem tells you that the general fiber will be smooth. So look at smooth fibers and let x1, xi, inside of xyi be a point. Then if you know there exists a single section, then it follows that there exists a section through all of these points. Such that s of yi equals xi for each I. So now going back to this question, we choose 2 points, x1, x2, and x, 2 general points. They map to 2 general points, y1, y2 of y. And then because y is rationally connected, there's some rational curve in y containing y1, y2. We restrict our fibration over that curve. So now we have a rationally connected fibration over a curve. We have these 2 points.